This is a very short screencast about a very important electronic device called the transformer. One type or model or example of a transformer is pictured over here on the right. What a transformer is two coils of wire that are not connected to each other. Usually there's some kind of soft iron core, pictured right here, that connects the two together. In class, you might recall that I had two solenoids. One solenoid was red, one was green in terms of the color of the insulation on the wires, and the one coil could be inserted into the other coil, and then through the middle of both coils, I had an iron rod that helped to enhance the effect that we're going to be talking about. Now, the first coil, called the primary coil, is the coil that is connected to the source of electricity. And the second coil, called the secondary coil, is the coil that is connected to the output, where work can be done. For example, on a resistor or a light bulb, or to scale it up to power a town or a city. The primary input is connected to the power source, which could be a nuclear power plant, a steam generator of some type, windmills, water mills, all kinds of ways to generate electricity. And you can see it's alternating current. This circle right here that has a sine wave in it represents alternating current. And in the United States, it alternates at 60 times per second, or 60 hertz. In other countries, for example, South America, it's 50 hertz. And you better know that if you're traveling to another continent that uses a different frequency of electrical energy generation, because something like an electrical shaver either won't work or will malfunction or might have a switch on it that allows you to adjust for a different country's frequency of electrical energy generation. Now, as the current is alternating, right here, as it alternates 60 times a second, the electromagnetic field, the magnetic field that surrounds the wire, is going to expand and collapse 60 times a second. And so as a result of expanding and collapsing, you have moving magnetic flux lines. And those moving magnetic flux lines, as they expand into existence from nothing, and then when they collapse back to zero, in a sense, break through or cross through the wire that's in their presence, in the presence of the magnetic field. And that induces a current in the wire. So I'm going to switch colors here. So as this electricity goes over the top and back around again and back around again and back, it's inducing an electrical current in the soft iron square, or it could be a rod. And of course, that current is going to go one direction, and then it's going to go the other direction 60 times a second as the magnetic field collapses and expands 60 times a second, which in turn then is going to create or induce a current in this coil right there. And that electricity then, alternating current, is going to go through your load and operate whatever is represented by this resistor right there. Now you'll notice in the original picture, I'm going to erase some of this. You'll notice in this original picture that we have 1, 2, 3 wires on the left, and we have 1, 2, 3, 4 wires on the right. And this is just an example. The number of wires on each side could be the same. The number of wires on one side could be hundreds or thousands, just like on the other side. Usually you have a rather distinct difference between the number of wires in the primary solenoid or loop and the number of wires on the secondary. Now, there's a reason for that. And this allows you to either increase the voltage. You can go from a small voltage to a big voltage when you go from a few number of loops of wire on the left side compared to lots on the right. Or, and again I'm going to erase this, you can also go from lots of wires on the left side, a big voltage, and just have a few number of wires on the other side, which is a small voltage. Now your initial instinct might be, are you creating or destroying energy in the process? And as you'll see in a few minutes, absolutely not, of course. Now, the operating equation here is that this change in voltage that is going to occur depends directly on the number of wires in the solenoid or loop. So if you have lots and lots of wires, you can induce a rather high voltage. If you only have a few wires, you can induce a rather small voltage. And this part right here reminds us that the current going through the wire is going to depend upon the strength of the magnetic field and the amount of those flux lines representing the magnetic field that are collapsing or expanding past the wire in a certain period of time. So this would be the breaking of the magnetic flux lines per second, for example, as a period of time. And we can say the same thing about the voltage on the other side, in the secondary. Now, there are a number of ways then to put these two equations together. And when you put these two equations together, you get this equation here. One way to write it would be like this, that the change in voltage in the primary compared to the number of turns in the primary will be the same value as a fraction of the change in voltage in the secondary compared to the number of turns of wire in the secondary. Sometimes you're going to see this particular equation written like this, where you might have a change in voltage 1 over N1 equaling the change in voltage 2 over N2. And of course you could take the reciprocal of that as well, which this looks just like I drew it over here originally. You can have the reciprocal of that. Now, what this means is that if we go from a few wires to lots and lots of wires in the secondary, that's called a step-up transformer, because you're stepping up the voltage from low voltage to high voltage. And if you go from lots of wires in the primary to just a few wires in the secondary, that's called a step-down transformer. Now you might ask, why would we even need to do this? So here's the idea. Back at the power company, let's pretend it's Callaway Nuclear Power Plant, or the Labadie Coal Power Plant that's nearby. Two of the places where St. Louis gets our electrical energy. When the electrical energy is produced by rotating coils of wire past magnets, it is at a very low voltage. It's at a low voltage, but a huge current. Now, if we were to immediately send that current, that electricity, through the wires at this super high current, all of that current plowing through the wire would produce a tremendous amount of heat, and there would be a tremendous amount of electrical energy loss. So what they do right outside the power plant is a huge area, sometimes several acres in size, filled with transformers. And these transformers take the electricity produced by the generating plant with a small number of turns of wire, and they send it to the secondary, and the secondary would have a huge number of turns of wire, which greatly increases the voltage, but in the process reduces the current. And now you've got these high voltage power lines that can travel great distances across states and even across country, but at a very low current, thereby greatly reducing the amount of energy that you lose due to I squared R losses, which we talked about in an earlier chapter. And so by immediately sending all of this electricity into a transformer, you can either step up the electricity to a high voltage or step the electricity down to a low voltage. Now, once that electricity at high voltage gets to a local neighborhood or community, then it'll go to another place. It's usually fenced in with a tall fence and maybe barbed wire across the top and a sign that says danger high voltage. And inside will be all of these metal boxes that sometimes have these like metal fins that stick out to the side to help dissipate any heat that might be generated. And they will step the current back down again. So in other words, they will increase the voltage by decreasing the current. And as a result, the voltage on the other side is going to go down and increase the current. And you can go either way with this, but you generally want to step the voltage down from the high voltage to a lower voltage. And then the electricity goes either underground or along power lines or sometimes on telephone pole lines to the various houses. Then when the electricity goes into the house and gets distributed around the house, different appliances have different transformers that are very small. A lot of times these transformers are no bigger than this box that I'm drawing right here. They might be that size, they might be maybe twice as big, twice as small. And these transformers can either step the voltage up to high voltage again, such as might be needed in some electronic devices, especially the old-fashioned television sets with their cathode ray tubes, a needed high voltage. Or they might step the voltage way down even farther to say a small transformer that could provide the low voltage necessary for, let's say, a doorbell. So you got transformers all over the place. And so here's our equation right here. What we're basically saying is that the power that comes in equals the power that goes out, because power is voltage times current. And you can either have high current, low voltage, or you can have low current and high voltage, depending upon whether you're going from a few turns of wire to a lot in the secondary, or lots of turns of wire in the primary to just a few in the secondary. Now, transformers are really, really efficient. Transformers can be upwards of 99% efficient because there's no mechanically moving parts. The only thing that's moving are these magnetic fields as they expand and collapse, inducing current in the wires. And therefore, the amount of energy that you lose is very, very small and primarily dependent upon these I squared R losses. And you'll notice that it's I squared, which means if you double the current, your I squared loss can be 4 times greater, 2 squared times greater. If you triple the current, it can be 9 times greater in terms of the amount of energy you lose. Now, to be honest, there's a limit to how high a voltage you want, because of course the greater the change in voltage between one wire and another wire, or between one wire and the ground, can create problems should something come in contact with 2 wires at the same time that are separated by a large difference in voltage. And so even the electricity that we pay for that originates in a power plant, sometimes 10 to 20% of that electrical energy that is generated is lost due to the friction, if you will, the resistance of just plowing through the wire, which of course shows you the advantage that we will have someday if we're able to make massive quantities of conduit of wire that can, and you guessed it, superconduct. If we can do superconductivity and basically have almost zero energy loss, then we will be saving 10 to 20% of the electrical energy we generate every year. And down in this last paragraph, you can see some of the actual values. The voltage is stepped up to around almost 250,000 volts at the generating station. And then when it gets to a distribution center, and you might see that in various communities, it goes down to maybe 20,000 volts. And even in neighborhoods, at the corner of a bunch of properties, like there's one near my house, where there's 4 different properties that come together, and there's a green box, maybe twice the size of an electric grill. And that's another transformer. Or sometimes on a telephone pole, if this is a telephone pole, you might have a cylinder on that telephone pole, which is a transformer, to step the current, step the voltage down so it can enter your house at 120 volts.